Today, in this lesson, we'll focus our attention on double integrals. Okay, so here is the goal. By the end of the class, you should be able to evaluate a double integral and solve application problem related to double integrals. By the way, you know, double integral and sometimes triple integral, they are very useful in many fields: business, statistics, science, and engineering, to calculate volume, average value of a function, calculating the mass, etc. Okay, they are very useful in many fields. But in this lesson, we will focus our attention on business and economics application only. Okay. So one way to start the lesson would be, you know, we discuss about the definition and all these things, and then we solve problems. But here, I want to go a different direction. First, we'll try to learn the skill, how to evaluate the double integral. And once we know how to evaluate the double integral, how to calculate the double integral, then we'll go back and discuss about the true meaning of double integral. What is the geometrical significance? What is the geometrical meaning of double integral? We'll do that later, okay? So let's begin with example 1. Evaluate the integral double integral, also sketch the region of integration. Okay. Please listen very carefully. If you know how to do one problem, probably you'll be able to handle all the questions because the process is exactly the same. First of all, notice that there are two integral sign and there are two differential. So what it means is the inside integral, there is one inside integral and there is another outside integral. We always begin with inside integral first. Let me repeat that. In order to evaluate double or triple integral for that matter, we always begin from the inside integral. So let me just copy the question first. 0 to 3, 1 to 2, xy cubed minus x dy and dx. So the inside integral is this part. Always start with inside integral. So the inside integral is 1 to 2 xy cubed minus x dy. Guys, listen very carefully, okay? I need your undivided attention for the next 1 or 2 minutes. And once you know how to do one problem, then you'll handle all the problem because the process is the same. First thing first, always begin with inside integral. Now, here you notice that this is dy. What it means is we are trying to integrate this with respect to y. That means y is our variable. So in this case, this means we treat y as a variable, and x as constant. Just keep that in mind. Now, in this case, y is variable and x is constant. So I can also write this as x 1 to 2 y cubed dy minus x 1 to 2 dy. Because x, we treat them as a variable. I can put them separately. You don't have to later, but let us look at this way. Now x is constant, I just copy. Now this y cubed dy, the integration will be y power 4 over 4, and then this limit is for y. So y equals 1 to y equals 2. Okay, I suggest that you write down this y here because, I have seen in the exam, if they don't write this y and they just write 1 and 2, I saw that sometimes people get confused. They substitute this 1 and 2 for x. Okay, so to make things more clear, I suggest that you write down what is that limit for. So the limit is for y minus x, and then integration of dy is simply y. So this y equals 1 to y equals 2. Now you're going to get x, and then this will be 2 raised to power 4 over 4, or maybe you can write this way. You can write x over 4, and then now you have 2 raised to power 4 minus 1 raised to power 4. We are done with this part, and x. So here we have 2 minus 1. And how much do you get? Well, so this guy will be x over 4, and this is 2 times 2, 16 minus 1 is 15, minus this will be simply x. So we have 15 over 4x minus x, which means if you simplify it, you're going to get how much? 11x over 4. Okay, so the inside integral is 11 over 4x. So now we will substitute the value of inside integral. And what do you get? Well, so the outside integral will be 0 to 3. The whole thing we already calculated, which is 11 over 4x dx. That's it. So that means you can write 11 over 4, and the integration of x with respect to x will be x squared over 2, 0 to 3. Since there is only one variable, you don't have to write x equal to 0 to x equal to 3. It is understood. So you're going to get 11 over 8. So that's going to be 3 square minus 0 square, and which means how much do you get? This is 9 times 11 is 99 over 8. That's your answer. Now, are we done? Well, there is another part. Also, sketch the region of integration. What is region of integration? Let us sketch that. Okay, I'm going to do this here, region of integration. So notice that here, let me just copy that question again. 1 to 2, 0 to 3, xy cubed minus x dy dx. What it means is the inside limit. You see the inside integral has limit 1 to 2, and the inside differential is dy. So what it means is your region of integration will be y is from 1 to 2. Okay, so this limit is for y. So y minimum limit, the lower limit is 1 and the upper limit is 2. In the same way, the outside differential is dx, which means the outside is 0 to 3 is for x. Now, all you need to do is you need to draw this graph. Okay, so to draw the graph, I think you may want to consider the boundary line. So the boundary line will be so x boundary line is 0 to 3. So x is 0 is there, and the 1, 2, 3. So 3 is there. X, all the value between this, okay? Keep that in mind, 0 to 3. In the same way, y is 1 to 2. So y is, let's say this is your 1 and 2, 3. So this is your 2. So the y is from 1 to 2. So this part, let us draw that line. So x equal to 0 means this one, x equal to 3 means this one, x equals y equals to 1, that means this line, and y equals to 2, that means this line. Now y lies between 1 and 2, so this is your y right there, between 1 and 2, and x from 0 to 3, so this is your line. So that's the region of integration. This is called region of integration. Now notice that this region of integration is a rectangle, right? In this case, we got a rectangle. It is because both of these are numbers. So we got our region of integration is rectangle. Now, I want you to try the same problem from a different perspective. I switch this. Remember, earlier, our question was, what is the question? Our question was 0 to 3 and 1 to 2, x, y. Anyway, so our question, let me reverse the order of integration. So earlier, we are given 0 to 3, 1 to 2, xy cubed minus x dy dx. That was the question, right? In example 1. So this is given in example 1. Now, notice that in example 2, what I did is I switched the order. So earlier I have dy dx. And now I have dx dy. I switched the order. I changed the order. If you want to change the order, then you must make sure that the limit also will be changed. So here, in the previous example 1, y, the limit for y is 1 to 2 and limit for x is 0 to 3. Inside limit is for inside integral and outside is for outside. So in this case, I switch it. So dx is 0 to 3 and y is 1 to 2. Okay, I switch the limit and I switch the order of the integration. Now let us work it out. I want you to try this on your own, okay? So the question is here, 0 to 3, 1 to 2, xy cubed minus x dx dy. So first you may want to try the inside integral, okay? Inside integral, which is 0 to 3, xy cubed minus x dx. I want you to evaluate this integral. In this case, your x is the variable. We treat x as a variable, y as a constant. So basically, you can write this as y cubed 0 to 3 x dx minus 0 to 3 x dx. So it will be y cubed, it will be x squared over 2. And so this is for x, the limit is for x, minus this one is x squared over 2 and limit is for x equal to 0, x equals to 3. So we'll get y cubed over 2, and so you substitute the value 3 square minus 0 square minus 1 over 2, you get 3 square minus 0 square. So if you simplify it, you're going to get 3 times 3 is 9, y cubed, 9 over 2 y cubed minus 9 over 2. Right? Or you can write 9 over 2. If you take common, you're going to get y cubed minus 1. Any questions so far? Okay, so now if you are okay with that, I'm going to just substitute the value. Substituting value of inside integral. So I'm going to get 1 to 2 9 over 2 y cube minus 1 dy. Okay, 9 over 2 is constant. To make life easy, I'm writing that constant outside. You don't have to do that, but that makes life easy, okay? Then 9 over 2, it is a simple a piece of cake for you, right? It's simple now. So y cube with respect to y will be y cube, y power 4 divided by 4 minus y. So you'll get 1 to 2. Okay, it is, the limit is for y now. So 9 over 2, and so it'll be 2 cube over 4 minus 2 minus 1 power 4, not cube, 2 power 4, sorry. 2 power 4 over 4 minus 2, and then minus 1 power 4 over 4 minus 1. Okay, so that's going to give me 9 over 2. It is 16 over 4 is 4 minus 2, which is 2, minus, that's going to be 1 over 4 minus 1, which is 3 over 4. Positive 3 over 4, is that right? Yeah, positive 3 over 4. Now you got 9 over 2 times, this will be 11 over 4. So we got 99 over 8. Did we get the same answer? What was the answer in example 1? Let us check that. 99 over 8. And what do we get here? 99 over 8. So what do you think? What is your observation? Is it always true, or it just by accident we got the same result? What is your thought? Is it just a coincidence? Okay. All right, so we noticed that in the previous example, our answer is 99 over 8, and here also 99 over 8. And the question is it always true? Yes, it is always true, provided that the region of integration is rectangle. If you draw the region of integration for this, okay, for this you get the same rectangle as before, region of integration. So if the region of integration is rectangle like this, then the case is always true. Switching the order does not make any difference. And guys, we are not the only one who figured this out first, okay? We are not the only one who discovered right now. There are so many people, they discovered this concept long time ago. And this Fibini, and we have the Fibini's theorem. So people already worked on this idea. So what is Fibini's theorem? The Fibini's theorem tells us that a to b, c to d, fxy, dy, dx, and now we change the order dx, dy. They are equal provided the region of integration is rectangle. What it means is all the limits are numbers, constant. Okay, if all the numbers are constant, then this relation always works. But if the limits involve some variable, then this relation doesn't work. Let me repeat that again. Here is the Fibini's theorem. So the theorem tells us that in the case of double integral, switching the order of integration does not make any difference in the final result if the region of integration is a rectangle. In another word, if the limits involve numbers only, constant only. But if any one of the limit involves variable, then this is not true. Keep in mind. Any question, guys, so far? So I want you to try this example 3 on your own, okay? So thank you guys. Example 3, you already calculated and the answer is 17/6, and that is the correct answer. And all right, now the question is, well, you already know how to evaluate the double integral with with a rectangular region of integration. In other words, when we have all these limits involve the numbers or constant, then you know how to evaluate the integral. Now the question is there any application in the real world situation? Can we apply this concept to solve some of the real world problems? The answer, of course, is yes. And let us take one simple example. Example 5. But before we start example 5, recall the average value formula from previous module. We have discussed that, okay? Average value for function of one variable, if we have a function, let's say, function of one variable, y equals f of x, then the average value is given by this formula. We know that. Do you guys still remember this formula? Average value of the function is 1 over b minus a integration a to the b f of x dx. Now, when we have two variables, function of two variable, we can extend this idea 1 over b. Okay, let us suppose that in this case the region of integration is from a to b and c to d. Okay, x between a and b, y between c and d. Then we can extend this formula. 1 over b minus a is for x, 1 over d minus c is for y, and then the integration a to b is for x and c to d is for y. So inside integral is for inside differential, outside integral is for outside differential. So we have this formula, okay? Easily we can extend that formula to this one. Now, using that formula, let us try to solve this example 5. A production function is given by, this is a similar production function, similar questions we discussed earlier in partial derivative. Cobb-Douglas production function, right? So it's the same kind. So we are given a production function given by 500 x raised to power 0.2, y raised to power 0.8, and the limit for x is 10 to 50 and limit for y is 20 to 40. And we want to find the average value, average production level, okay? So that means all you need to do is average is given by, I'll write PAV equals 1 over B minus A D minus C and integration A to B C to D, the function in this case pxy dy dx. That's the formula. And here what is given here is that production function is given, which is 500 x raised to power 0.2, y raised to power 0.8, and then your a is given. This is your a, this is your b, this is your c, this is your d. So a equals 10, b equals 50, c equals 20, and d equals 40. So substitute the value and then you'll be able to solve it without any difficulty. Therefore, PAV average value equals 1 over B is 50 minus 10 times 40 minus 20 is 10 to 50 and then 20 to 40, and the function is 500. To make life easy, I'll write 500 here. Okay, I'll write 500 here, and then x raised to power 0.2, y raised to power 0.8, dy dx. Now guys, I want you to complete this on your own, okay? So first start with inside integral. Inside integral is 20 to 40 x raised to power 0.2, y raised to power 0.8 dy. So remember, in this case, we treat y as a variable and x as a constant. Therefore, if you want, you can write this x outside if you like. So this means you can write x 0.2 is just constant. I just copy as it is. Now you have y. This will be 1.8 over 1.8 and y from 20 to 40. And so you're going to get x 0.2 over 1.8. And here you will have 40 raised to power 1.8 minus 20 raised to power 1.8. All right, now this is the value. If you want, you can actually calculate using your calculator, but I don't have calculator right now, so I just leave it like this. And so what you can do is this guy will be 500, and in the bottom, this will be 40 times 20. I believe that's 800, right? Can I write simply 5 over 8? This side will be 5 over 8. And substituting the value of inside integral, you're going to get 20 to 40 there, and the inside integral is x raised to, okay, I will write all the, okay, 0.2 over 1.8, and we have 40 raised to power 1.8 minus 20 raised to power 1.8 dx. So let me write down all the constant outside to make life easy. I'll get 5 over 8 times 1.8, okay, times 1.8 in the bottom. And then we have 40, 1.8 is constant. I just copy all the constant as it is. All you need to do is just evaluate this integral, x raised to power 0.2 dx. Okay, evaluate this and let me know what is the answer. I'll wait for you. I trust you guys can handle this easily. Okay, anyway, so you can do that later. And if you have any question, let me know. Otherwise, let us move further. Now, the question is, so far we deal with just the rectangular region of integration. Okay, rectangular region of integration. So we will talk about the general, double integral over general region later. But now the question is, we know how to evaluate the double integral, but what is the meaning of it? What does it mean? Geometrical meaning of double integral. Let us look at that, okay? So geometrical meaning of double integral is, let me go all the way up. Notice that the integral of one variable, function of one variable. For example, if we have a to b, f of x dx, what this represent is area under the curve, right? It represent area under the curve from A to B. And how we did this, how we developed this idea is by using the Riemann sum. What we did is we have a curve and we want to find the area under the curve, and we divided this into many small rectangle or trapezium, or and what we did is we find the area of one rectangle plus another rectangle plus another rectangle, and we find the sum of all of them, and we ended up having Riemann sum. And so the Riemann sum was this: I runs from 1 to n, f of xi delta x. That's what we got. And when we take the limit n tends to infinity, then it actually gives the exact area. So we say that definite integral represent the area under the curve. Using the same idea, now we are talking about 3 dimension because our function is z equals f of xy. So when we are talking about function of 2 variable, we are talking about 3 dimension. In the 3 dimension, what you get is, this is the figure. Okay, this is the solid. And if you divide that solid into a bunch of small pieces, what you get is, you'll get this kind of piece, like a box. Okay, this is a box. And the mathematical word for that is parallelepiped. Okay, we get a parallelepiped. So this parallelepiped is just one piece out of that. I divided this solid into many pieces, many boxes, and I just choose one box here. Now what I would like to do is, you see, this one is your delta x, this one is your delta y, this one is your delta x, and this is your f. So if I do f xy, delta x, delta y, and delta x, what do I get? This is your height, this is your length, this is your width. Length times width times height, what is that? Clearly this is a volume, right? Thank you. It's a volume. So volume of one box is given by this. And there are infinitely many boxes there. Okay, so I sum all of them up. See here, I find the sum of all of the boxes. And then this is a Riemann sum, and we know that for Riemann sum, we can write definite integral. Because there are 2 variables x and y, so we use the 2 summation notation, one for delta y, another for delta x. And so we can write this as a Riemann sum, which is actually the integral, definite integral, in this case, double integral. So basically, double integral gives us the volume. Okay, keep that in mind. The single integral, definite integral, gives us the area, whereas the double definite integral gives us the volume under the curve. Does that make sense? So in example 4, we are asked to find the volume under the surface f of xy, which is given by this function, and above the region R, given by the region of integration is given by this, x from 0 to 2 and y from 0 to 2. Okay, so the volume will be we know that volume is, it's a double integral a to b c to d f of xy dx dy. Notice that x is the interval for x is a and b and y is c and d. Or we can also write the same thing, because it is a rectangular region. That means all the limit involves the number. We can also write this as c to d, a to b, f of xy, dy dx. Okay, dy, notice that dy dx. Therefore, since dy is the inside differential, which is for inside integral, note that the limit is c and d. Okay, here where x between a and b and y between c and d. Either you write this or that, doesn't matter. Now sometimes one way is easier to deal with, to evaluate, than the other one. And in this case, I don't know yet. Let's look at which one will be easier. Okay, so the volume will be, you can either go from 0 to 2, 0 to 2, 6x power 5 e raised to power x cube y dx dy, or we can write 0 to 2, 0 to 2 6x cube e raised to power x cube y dy dx. Now, which one? I want you to try both of these by both method. Okay, let me do one together, and I will leave the other one for yourself. So let us work. Which one first? Maybe let's work this first. Okay, let's work this way. Let us consider that we want to consider this one here. So v equals 0 to 2, 0 to 2, 6x cube e raised to power x cube y dy dx. Now first we need to find the inside integral, which is 0 to 2, 6x cube e to the x cube y dy. So in this case, notice that we treat y as a variable and x as a constant. So I'll write this 6x cube is constant. I'll just copy this outside, and 0 to 2 e x cube y dy. So 6x cube, and this guy will be e raised to power x cube is constant. So now the question is, if we have e kx dx, what is the integration? You know that this will be e kx over k, right? Well, see, you know this. And this x cube is a constant. We consider x as a constant. Therefore, you can consider as a, as just like k. So this over x cube. And then you have y is your variable. So y equals 0 to y equals 2. Does that make sense to everyone? Now you can cancel this x cube and x cube, so that what you get here is 6 and substitute the value. So e raised to power x cube, y means 2, so you can write 2x cube minus e raised to power 0. So that's going to give me 6 e 2x cube minus 1. That's it. Okay, guys, I copied the wrong thing. So the question is 6x. Thank you for pointing this out. 6x raised to power 5. So this one is 6x raised to power 5. This is raised to power 5. This is raised to power 5. I told you I'm not good at copying the thing. So you need, sometimes I do it intentionally to check whether you are paying attention or not. Sometimes I forget. And anyway, thank you for reminding this. And so this is actually x power 5. So I will have 6x squared here. And then this one, so that means the inside integral is 6x squared and this, okay? Or if you want, you can simply write 6x squared e raised to power 2x cubed minus 6x squared. You can write that. You can just, you don't have to put this inside the bracket. You can put that like that. Okay, now let us substitute the value. So the inside integral is this, the whole part right here we already calculated. So let us substitute the value. So we're going to get 0 to 2. So we get 6x squared e raised to power, maybe I think we'll write this way, that make life easy. So let us just substitute this way, 6x squared e raised to power 2x cubed minus 1 dx. Okay, all we need to do is evaluate this integral. Now this becomes a one variable, okay, single variable integral problem. So what do you want to consider here? Well, let us suppose that u equals 2x cubed, then your du will be 6x squared dx, and the limit, we need to change the limit when x equal to 0, u equals to 0. When x equals to 2, your u equals to 16. So basically this integral will change into 0 to 16. 6x squared dx is 6x squared dx is du, so that's going to give me e raised to power u minus 1 du. All right, that's what we get. So now with respect to u, this answer will be eu remains the same, eu minus u, and 0 to 16. So you're going to get e raised to power 16 minus 16 and minus e raised to power 0 minus 0. So what we got here is that e raised to power 16 minus 17, right? Because this will be e raised to power 16 minus 16 minus e raised to power 0 is 1. So your final answer is this. Any questions so far? Now, I want you to try this using this order of integration. And we want to check which one will make life easy, okay? Whether this method is easy or this method is easy, I don't know yet. So I want you to try this part on your own, just for fun, okay? And let me know which method will make life easy, which one is easier to deal with. So if you want to deal with this, so your inside integral will be, inside integral is going to be 0 to 2, 6x power 5 e raised to power x cubed y dx. But integrating this with respect to x is not easy, okay? It's very difficult, I'm telling you. Sometimes, you know, in some other situation it may be impossible, but here it's, for this particular question, it's going to be very difficult. So I don't suggest using this order. So from this example, what we know is that sometimes order makes things easier or difficult. What order you choose will make your life easy or difficult. And my advice always is choose the order that makes your life easy, that makes the calculation easy, okay? All right. So we're going to do the integration, double integration over the general region next day, next class.